So I'll be posting the homework today, so don't worry about that. You'll get some homework in if anyone's been missing it. Class is going very quickly. The final day of class is a week from Wednesday. It always just goes by in the blink of an eye right after Thanksgiving. So that's going to be it, unfortunately. So paper project will be due a couple days after the final. I mean, you're fully welcome to submit it beforehand, but since we're doing the final, switching around a little bit, giving you guys a few extra days, I thought was a better way to juggle that. But again, so the main thing with this project, what I'm looking for is I'm looking for a good dissection of the paper in a sort of more lay term perspective. I mean, lay in terms of traditional chemical engineering language. Because oftentimes when you read these thermo papers, it's a small, tight-knit community. They have really terse ways of describing what's going on. And so if you looked at the papers, you actually read through the papers that were included on the homework a couple times ago, or was it last time? I don't remember exactly when. But you'll read through it, and how they don't tell you at all how they actually did the modeling, right? The assumptions were really, really hidden in there, if they were mentioned at all. And so the language in the thermo community is sort of a different beast. So what I'm really looking for is you to translate it to me, so that if I read through the paper and I feel confident that you have a good understanding, then I don't have to go to the paper itself and figure out what is actually going on. So if I have to crack open the paper to say, okay, what? This is so confusing. How does this equation relate to this one? Then I have to go to the paper. Then that's going to be sort of a mark of it wasn't as streamlined as I would have hoped. And so any hard, aggressive calculations, you're free to put them in an appendix, right? So make sure you give me a complete story, and if it has to be more than those 4 pages, structure it in such a way that some sections can be offloaded to an appendix, details in the derivation and whatnot. And so when I get to that point, I say, I'd like to learn a little bit more about this, and I can go to the appendix. Everyone clear on that? Okay, so I'm not looking for a dissertation. I'm really looking for a book report. So as a reminder of where we've come, so what we've done so far when we've talked about StatMech, and remember the overarching goal of what we're trying to do here is essentially, if we assume that the universe is made up of particles and all the properties of matter all distill down to how different particles interact, which is indeed, from a classical perspective, that's how it interacts. From a quantum perspective, we're all waves and how waves interact. But from a classical perspective, which is, for the most part in chemical engineering, a totally sufficient way. Now, looking at absorptive processes or heterogeneous catalysis, their quantum effects become significantly more important with a lot of exchanges of electrons. But for bulk kind of properties, quantum effects are not necessarily all that critical. So from a classical perspective, what we're trying to do with StatMech is we're trying to go from assuming the universe is a collection of particles how do we take that information of how the individual particles interact and predict macroscopic properties? So what we've done basically so far is defined the rules of the game. So we defined ensembles. The canonical ensemble and the T. We define the microcanonical ensemble and the E. And then from these ensembles, we were able to go from the partition function to enthalpy, Helmholtz energy, internal energy, entropy, and so on and so forth. And we were able to do this for relatively simple systems. And so right now, we've applied this to non-interacting gases. but the rules that we've defined for the most part will hold true. The canonical ensemble is most directly related to the Helmholtz energy, which makes sense because this is exactly the macroscopic thermodynamic variables associated with the Helmholtz. Right? The microcanonical ensemble is directly related to the entropy, and this makes sense because these are the variables. Right? In terms of how we defined macroscopic thermodynamics, we basically said there were three fundamental variables: entropy, volume, and energy. Right? Entropy is the one missing from here, but we could also say N. In terms of classical thermo, we don't ever actually really have to define N for a single component system. We can always just make everything an intensive property like density. So the problem now, so what we've done so far is we've looked at how we can build up properties of single isolated molecules. That's really what an ideal gas is. So we talked about monatomic particles zipping through space only with translation. Then we talked about diatomic particles having multiple different energy modes and how we can use that information to build up all the properties, calculate the heat capacities, using models taken from quantum mechanics. Harmonic oscillator, rigid rotor, right? Particle in a box. And with those rules, we were able to build it up. Now basically, for non-interacting particles, you just do that lots of times over again and it gets more complicated. So that kind of wraps up that interactions. So now, what we're going to transition into is really the fun part. Is interacting particles. What we're going to be covering with interacting particles is the models get to be significantly more complicated, and they're really only valid under certain circumstances as well. So what we're going to be talking about when we're dealing with interacting particles is the key assumptions that we make in calculations, and then transition us into how we do modern thermodynamic calculations, which is predominantly molecular level simulations. And these are the core assumptions that go into 99.9% of all molecular simulations, so that when you leave the class and you see a paper talking about a Monte Carlo or an MD, or you look at a structure factor or a radial distribution function, that these terms don't seem out of the ordinary, because that's really how we communicate information about the molecular level scale. So, for non-interacting particles, we did particle in a box, in which case the energy of some state I was based on mass of the particle, the volume, and some quantum numbers. So from here we were able to calculate a partition function. Now if we take a collection of particles that are indistinguishable, the partition function of the collection is equal to the partition function of an individual particle multiplied by the number of particles, raised to the power of the number of particles, so q times q times q times q, and then normalized by an indistinguishability factor. So if we then consider capital E here to be the energy state of a collection of particles, if we assume that they're non-interacting, we're effectively saying we're just adding up all of the individual energy from all of the individual particles. Right? That's the idea behind the non-interacting. That's how we built our entire partition function, and that's how we were able to derive the ideal gas law and other ideal gas properties. Now, however, if we have interactions between particles, this relationship no longer holds true. The total energy of the system is not just the energy of the individual particles themselves together. So with interactions, the energy of the combined total system is going to be equal to all of the energy of all of the individual particles plus a contribution of, let's see, I'll write U, let's see, I'll write this way. Some function that tells us what the energy is based on the positions of all of the molecules relative to one another. Let's see, do I have a fancy name for that? So what I'm going to abbreviate here is that this Rn is going to be equal to the collection of all of the position vectors. So if I am looking at a material, I'll just draw it in 2D space, right, where I have x and y, and I have a particle at some position. If this is particle 1, that's going to be R1. If this is particle 2, R2. So these are just position vectors telling us where the particles are located. So if we have interactions, we have the energy contained within the velocities, rotations, vibrations, all the different internal energy modes associated with an individual isolated particle, plus we have a contribution associated with the collective positions. Let's say we have electrostatic sites, right? There's going to be attraction and going to be repulsion. If you get too close together, the electron clouds are going to overlap and they're going to want to repel. Far apart, van der Waals forces tend to pull things together, or hydrogen bonds, permanent dipoles, things like that. So that's all of the information about all of the interesting properties of matter are contained within this term right here. So this is going to be the emphasis in the future. We, in a couple of days of class, basically handled all of the different ways that we could store energy in an isolated, simple molecule. So with interactions, the partition function becomes significantly more complicated. So I truncated this a little bit in terms of the math. Okay, so this here is our contribution from the isolated individual particles. All right, so up until about here. C is a constant, and we're going to set this to be v to the minus n. And this term right here, we call it z. This is called the configuration integral. Let's take a second and dissect what's going on here. So, what this term is, now remember the partition function in terms of words that we can understand. What is the partition function again? How would we describe it? To remind ourselves how we can walk through what this configuration integral means. Who wants to volunteer and answer? What is the partition function?
It's a scale of the summation of all the states.
Exactly. Right, so what it is, in terms of the canonical, so effectively it's all of the possible states. Now in the canonical partition function, that means you scale it by a Boltzmann factor. So this expression here, right, everything up to the Vn, this corresponds to all of the possible single particle energy states that are available. What is the vibrational mode? What is the translational mode? What is the rotational mode? In this case, it's a monatomic system, so I guess it's only translations. Right? This is simplified for an ideal monatomic gas. I guess I should clarify that. This expression, we haven't been able to integrate it yet because we still have the Boltzmann factor, or the Boltzmann distribution, E to the energy of the configuration normalized by kBT. So this URN, this is the potential energy that is based on all of the relative positions of the particles. So if I have particle 1 and particle 2 here, are they attractive or are they repulsive? Do they have potential energy? And so the way you can get potential energy from a force, if you have two, let's say, positive charges that are really far apart, and I push them together and I push them together, they don't want to go together. At infinite separation, there's no forces on them because the force interaction drops off to a power law of 1 over r squared. So as I push these two particles together, I'm giving the system energy. And if I push them together and I hold them in a position like this, they're going to have potential energy. If I let go, they're going to shoot apart. If I have a negative charge and a positive charge, they're going to want to come together. So I'm going to lose energy when I bring them together. Right? So pulling them apart takes energy. So that's what this configuration integral tells us. If I have positive and negative charges distributed throughout my system, there's going to be potential energy stored in those interactions. Further, van der Waals, induced dipole interactions, those are all going to be attractive forces. When the electrons overlap, that's going to be a repulsive force. All of that information about whether or not the electron clouds are overlapping, whether or not the positive charges are near to each other, whether or not the positive and negative are near to each other, all that information is contained right in this integral. But the problem is, I have a box with a mole's worth of particles. So particle 1 can be in any location in the box. Particle 2 can be in any location in the box. So this integral here is this integral drn, which is actually a collection of all of the position vectors. So what I'm saying here is I'm going to move every particle into every other possible configuration along with every other particle being moved into every other possible configuration. And at every single one of those positions, there is an energy associated with the interactions. So if I have relatively simple 10 particles, that means this is going to be 10 integrals. I'm going to hold the position fixed of particles 2 through 9 and then move 1 everywhere. Then I'm going to hold the positions of 1 through 1 and then 3 through 9 and then move 2 around everywhere. Right? So I'm only going to move 1 particle at a time for all of the fixed positions of all the other particles. Conceptually, does it make sense what this integral is communicating? We're not going to attempt to integrate it because this is far too cumbersome of a procedure. So what we do is we introduce simplifications. Now the reason for why we have this constant of integration, so it cancels out, is because if U associated with all of the positions is equal to 0, then the configuration integral gives us back that term. So if this is 0, okay, so e to the 0 is 1. All I'm doing is integrating over volume of 1, which just gives us the volume. And then we do that n times over again. So that gives us volume times volume times volume times volume times volume, all the way up to n number of particles. When we're dealing with sort of these statistical type calculations, a lot of the times, the governing equation that we'll be using is far too complicated to directly process, but one of the key things is being able to look at a seemingly very complex equation, at least breaking it down into what the physics that it's trying to communicate are. But in terms of actually applying this, no, we can't do that. Okay, so for the canonical partition function, the Helmholtz energy is directly related to the partition function itself. From classical thermo, the pressure is related to the first derivative of the Helmholtz with respect to volume. Which means that there is no volume term here anymore for the particle in a box. It's all been lumped into the configuration integral. Which means that so that means that all of the interesting information contained, at least with respect to pressure, for an equation of state, everything gets lumped into the configuration integral. Because when we take the natural log of Q, that goes to 0, that goes to 0, that goes to 0, that goes to 0, right? Because you're adding, when you take the natural log of something, anything that's multiplied together becomes added. Then when you take the derivative with respect to volume, it goes to 0. So only Z has any information associated with the volume of the system. So now the configuration integral is the only thing that matters when it comes to the behaviors of a fluid. Okay. Now the next question is, what do we do with this thing? So we are going to simplify the configuration integral. So that is our goal. Okay, so we have, let's assume we have a system of 3 particles. This marker's dead. Okay. So what we're going to say is that the internal energy, or the potential energy, of the system, in this case, it's going to be a function of the positions of each of these 3 particles. What we're going to assume, actually, we don't have to assume this right. So what we're going to say is we're going to write this down as the energy associated with the relative positions between 1 and 2. So in this case here, right, this would be R1, 2. Let's just do it this way. Let's just do the absolute value. I don't have to worry about the order. Okay, so we're going to say that it's only the distance between these 2 particles that determines the energy associated with these 2 interactions. Likewise, 1, 3, U, 2, R2, 3. And then we're going to have to add in the correction factor. So let's recap. This is R13. This is R23. So you have 3 particles. Some might be attracted, some might be repelled. We don't have to worry about that right now. So what we're saying then is that the energy that's contained within the configuration of the particles in the system, which is just the configuration integral, all we're doing is we're simplifying this down for a system of 3 particles. We're saying it's the energy associated with the interactions between 1 and 2, interactions between 1 and 3, and interactions between 2 and 3, whether attractive or repulsive. And then we're adding in a final correction factor that's based on the relative positions of all 3 of them. So here's the key assumption that we're going to make for most all calculations. The assumption is pairwise additivity. So what this means is that the internal energy or the potential energy that is not associated with the direct binary pairs of particles is approximately equal to 0. Now this is the assumption that is used in virtually all molecular level calculations. The potential energy based on the configuration is just the total summed up energy of particle 1 with all the other particles, particle 2 with all the other particles, particle 3 with all the other particles. And then we say that is the potential energy or the internal energy of the system that's associated with the configurations. So this is a very, very critical key assumption that is used basically universally. The reason for that is because this is very hard to evaluate. So this is our best strategy to solve it. So with this assumption, the configuration integral can be rewritten. We still have to integrate over all of the different positions, but instead it looks a lot meaner than it actually is. We'll take a second and we'll break this down. Okay, let's take a second and break this down. We're integrating over all of the particle positions for all of the particles. But in this case, what we've done is we've taken advantage of exponent properties. Because if we say that the internal energy or the potential energy is just summing up all of the pairs of interactions, if I sum up the pairs inside of an exponent, that's like multiplying them on the outside of an exponent. So this term right here is basically counting all of the binary pairs, starting with I equals 1, and then J has to be 2, 3, 4, 5, 6, 7, 8, 9, 10, and then once I is 2, then this one is going to be, wait, hold on, did I write this right? Sorry. This is even more complicated than I meant it to be. I less than or equal to I. There we go. I missed something there. So if I is 2, that means J has to be 3, 4, 5, 6, 7, 8, 9, 10. If I is 4, then J is 5, 6, 7, 8, 9, 10. So it's just a way you don't double count the energies of interactions, right? Because 1 and 2 are indistinguishable, so if I flip their positions, that's still the same potential energy. So this right here then simplifies our problem to only considering how do two particles attract or repel each other. So instead of having to worry about the relative positions of everything, the only thing we have to concern ourselves with right now is what is the potential energy based on the configuration of two particles relative to just the absolute value of the separation distance between the two of them. How does everyone feel about that? Okay. Okay, let's think about the properties of what this function would have to be. As two particles get infinitely far apart, right? This is R, I, J goes to infinity. What should the potential energy of the system be?
10 to 0.
It should tend to 0. There should be no interactions because they're so far away. That's effectively an ideal gas state. As they get closer and closer and closer together, what should happen? Should they attract? Should they repel? What should happen as you start to overlap two particles? They should repel each other very aggressively. So this gives us two limiting cases of what's going on. So let's look at some examples of these. So we typically will call this an intermolecular potential, or interparticle, or something along those lines. Potential is the key word here. This tells us what is the energy based on how close or far apart they are. Does anybody know some potentials off the top of their heads? How particles interact? Leonard Joules is one. Any others? Hard sphere potential? You guys heard of that one? Okay, so hard sphere potential. We plot out separation distance on the x-axis and the potential energy on the y-axis. At some value sigma, now this is associated with the radius of the particle. We have a function that goes to infinity, and it is 0 everywhere else. So the hard sphere potential is equal to a piecewise function where it is infinity for r, I, j less than or equal to sigma, and 0 for r, I, j greater than sigma. So let's say, for example, we wanted to know what is the radius of a neon atom, right? We know that there is no effective radius, right? There is no radius, right? You just have a decrease in the probability of finding an electron the further away you get from a certain separation distance. But in theory, we could apply a hard sphere model and then tune it such that we can tune the sigma to best match the properties. Does that make sense? So it's a little akin to an equation of state approach, right, where we have had to make some assumptions on how particles interact. But the assumptions that we're making now, they're not these fanciful assumptions about how should H change with respect to T and whatnot. We're actually talking about the properties of the particles and how to best model the properties of the particles. Okay, another common potential. is the square well potential. In this case here, we have a similar behavior at low separation distances. It goes to infinity at some value of sigma, but there is some attraction. This here is R square well sigma. So this is at some R separation distance, and the SW is for square well, and that's the sigma. So we can write out the potential for the square well potential as a piecewise function as well. In this case, it's going to be infinity so long as R is less than or equal to sigma. It's going to be negative epsilon when you're in the square well region. And then it's going to be 0 beyond some R square well. So in this case here, our particles are not going to interact, then they're going to be attractive, and then they're going to be infinitely repulsive when those electron clouds begin to overlap. So the reason for these simplified potentials, turns out they're not particularly accurate, but they're used a lot. Right? These potentials are used a lot of times to discover fundamental properties of systems and matter. But the idea behind these simple piecewise functions is that it actually opens up the possibility that this configuration integral can actually be evaluated quantitatively. So that if we know how the particles interact, we could tune, in this case, our sigma, our epsilon, and how large our well depth is to better match real properties. So these ones here are not particularly useful if you want to predict real fluid properties, but if you're trying to understand, for example, the role of the shape of a particle or the role of a simplified system, right, these are really great opportunities to understand the fundamental physics of simplified systems. And again, this is why a lot of people back in the 60s, 70s, and 80s were doing cryogenic experiments on noble gas liquids, because you can actually fit them reasonably well with these simplified potentials. And so we can actually test the core fundamental assumptions of some of these stat mech processes that we're dealing with. Now, by far the most common potential being used in sort of I don't want to say real calculations, but calculations where you're actually trying to match experimental properties, is the 612 Leonard-Jones potential. So in this case here, we will draw this out. So I'm normalizing the potential by some factor here, which is epsilon, which is a parameter in the model. Don't have it in my mind. I'm pretty sure this is 1 where it crosses there. Where it starts to become, okay. Let me get the form here. U-R-I-J. This one's nice because it's a continuous function, so if you're not doing it analytically, if you're doing it analytically, a piecewise function is going to be much easier to evaluate. If you're doing it numerically on a computer, then a continuous function is going to be by far the easier of the two to operate. So what happens in the 612 Leonard-Jones, far away, particles are not attracted, they're not repulsed, they stick where they want to be. You have an attraction. Now this attraction here is the strength of it is proportional to 1 over r to the 6th power. Now this is analytically exactly what we would expect from London dispersion forces. So this would be attractive potential from induced dipoles. Once we reach some sort of ideal separation distance, if we start to get the particles closer and closer and closer together, they start to become net repulsive. So this term here, the 12, corresponds to the repulsion of those forces. Right here we have negative, meaning that you lower the energy of the system bringing it together. Positive, you raise the energy of the system by pushing them too close together. Now the reason for why it's a 612 potential is because 12 is 6 times 2. Meaning that this is a computationally relatively efficient potential to evaluate. So once you've calculated this one, all you have to do is raise it to the power of 2, which is a relatively computationally efficient procedure to do. So you don't have to recalculate a bunch of terms. Just take this term and square it, and you have this term. So that's the whole reason behind the 612 Lennard-Jones potential. There is no fancy science, it is literally just 6 squared. That's it. But this is what everyone uses. Okay, so what we're going to talk about, so I've got a bit more sort of hard maths to work through. But basically, with this information and the configuration integral, we can simplify this expression one more time, and we'll be deriving the virial equation of state. So the second virial coefficient can be analytically derived if we know the potential of interaction and we simplify this integration a little bit here. So we'll talk about that on Wednesday. But in the last few minutes of class, what I want to do is conceptually go over why I think this information is absolutely critical for basically any modern engineer or researcher to truly understand. So if we have a refrigeration cycle, okay? So in a refrigeration cycle, what we're doing is we're compressing a gas, and then we're expanding it. Now an ideal gas, right, and the key thing here is what they call the Joule-Thompson Coefficient. So what we're looking at is, let me see if I can get it right. What we want to know is the Joule-Thompson Coefficient of a system, which is typically denoted by mu. So this is how does the temperature change with a change in pressure while holding the enthalpy constant. So in the refrigeration cycle, this is a key step to getting the actual refrigeration process to run. How does the temperature change with respect to pressure when we're holding enthalpy constant? So for an ideal gas, and we want to venture a guess what the Joule-Thompson coefficient is for an ideal gas? What is the enthalpy a function of in an ideal gas? Only the temperature. There is no pressure dependence on the energy of the system. So a Joule-Thompson coefficient for an ideal gas is 0. So when you expand an ideal gas, isenthalpically, the temperature doesn't change, right? Because enthalpy is only a function of temperature. The temperature is only a function of enthalpy for an ideal gas. But for a real fluid, like a refrigerant, the Joule-Thompson coefficient is not 0. When you expand it, sometimes it heats up, sometimes it can actually cool down. So, let's take this example here. So let's assume we have a fluid that follows the Lennard-Jones potential. Now the two parameters that we don't know are this epsilon energy term and the sigma radius term. But presumably we could tune a model to match. So let's say, for example, we have two scenarios. I have a scenario where I have a gas that's really highly pressurized, and I'm trying to design a refrigeration cycle. So I want to go from this point A to this point A prime. Okay? I'm expanding it from a really compressed state, and I'm letting it open up a little bit. Alternatively, let's say I'm going from B to B prime. It's a slightly lower pressure, right? Because if the average separation distance, of course this is an average, so it's an oversimplification, a simplification, not over. right? If my average separation distance between particles is very close together, then I expand it in a Joule-Thompson valve, so isenthalpic valve, because I want to cool that gas down so that I can steal all the heat away from the cold items in your refrigerator and reject it out somewhere else and operate my refrigeration cycle. Do I want to go from A to A prime or from B to B prime? Right? So this is us not only designing a refrigeration cycle, but now we're designing a molecule, a refrigerant, and the pressure conditions that we operate this refrigeration cycle on. So this is way more detailed than what we were talking about with macroscopic thermodynamics, where we just had to guess and check and try a bunch of different properties. Now, we could potentially know exactly the intermolecular interactions necessary to understand which of these two would provide us a better refrigerant, which to me sounds like a really powerful design criteria. Okay, what does everyone think? Which one should we do here? Should we go from A to A prime or B to B prime? Which of these two will cool down my gas stream so that I can effectively operate a refrigerator? I can't use an ideal gas in a refrigeration cycle. I must use a non-ideal gas, and all non-ideality comes from particles interacting. Right? We could make the same argument here for a square well potential, potentially, but it's not as good. Any thoughts? What do you guys think? A to A prime? Okay, let's do a vote. Who says A to A prime? Who says B to B prime? Okay, so let's walk through this. So, if I'm going from A to A prime, right, my delta U, the change in my U, which we'll say it's roughly the same as delta H. So delta U is basically U2 minus U1, or in this case, let's say U A prime minus U of A. What's happening here is I'm going from a system of higher potential energy to a system of lower potential energy. Okay? Where does that energy go? Right? This energy was stored in the configuration of the particles. And now I've released the energy that was stored in the configuration of the particles. It has to go somewhere. The enthalpy change of the process has to equal 0. So this energy has to go to kinetic energy, meaning that you actually heat up your gas by expanding it. So in this case here, your temperature increases. Your expanding gas actually gets hotter. Now going from B to B prime, you're taking the system at an energy level that it's really quite happy with. You're at just the balance of attractive and repulsive forces that you're at a potential energy minimum or near it. So when you expand your gas from B to B prime, what it's having to do is you're now forcing those molecules to be in a higher energy state, right? They were down here at lower energy. Now you've raised the energy state. So in this case, you have to somehow give those particles more energy. So how you give them more energy is you take it away from their kinetic modes, their vibrational modes, their rotational modes in the form of temperature. So in this case, going from B to B prime, that will lower your temperature. So as a gas expands and it's non-ideal, right, for the most part, in general, it cools down, right? Because this is going to asymptotically slowly approach 0. So for most gases, as you expand them, you're going to be raising the potential energy based on the configuration of the particles in the system. But in some circumstances, if you compress it too much, then you'll actually be heating the gas as it expands because you've confined it so much that they're repulsive. Now there's a transition point here in the Joule-Thompson coefficient based on the pressure of the system where it will equal 0. And that's kind of an interesting marker to know at what pressures does a fluid behave as a good refrigerant or does a fluid behave as a bad refrigerant, right? Because you can, in theory, operate the refrigeration cycle where you're actually heating up the system as you expand it. But the key thing is here, thinking about how particles interact based on their individual properties is an immensely powerful consideration. So now what we can do, though, there's some analytical stuff that we can work on dealing with simplified potentials and the configuration integral. But that's a small minority of the possibilities. The real possibility is taking potentials like the Lennard-Jones potentials and other ones, and then instead of trying to analytically calculate the configuration integral, we're just going to say, you know what? I'm just going to put this whole thing in a computer and just have this be the rules of how particles are attractive or repulsive, and let the molecules wiggle around. That way, we can design a simulation that can predict macroscopic properties for any arbitrarily designed molecule we want, which is really powerful for the design process, but we have to make sure that those molecules and particles interact according to rules that we can tune. So now we don't have to argue about whether chemical A or chemical B is better. What we can do is we can argue now about how does a carbon interact with a hydrogen? How does an oxygen interact with a sulfur? And that simplifies the way that we can structure our arguments, because there's a lot fewer elements than there are molecular compounds, but unfortunately there's still a lot of elements. So it's not an easy property, an easy thing to deal with. But conceptually, this is one of the most important things I think I want people to take away from this class, is to start thinking about systems as interacting particles. And that's the whole power, I think, of StatMech, at least from an engineering perspective. Going into the nitty-gritty mathematics, manipulating this right here, I don't think are as helpful conceptually as looking through real examples of how we can actually apply these intermolecular forces. Any questions? So we're going to keep on talking about interacting systems from now until the end of class. Homework should be posted today. I'll send out a quick note when I get that online. And if nothing else, I will see you all on Wednesday. Thanks.